Let's do a torque question from a real FRQ. This one comes from 2024's AP Physics exam. The left end of a uniform beam of mass m and length L is attached to a wall by a hinge, as shown in figure 1. One end of a string with negligible mass is attached to the right end of a beam. The other end of the string is attached to a wall above the hinge at point 1. The beam remains horizontal. The hinge exerts a force on the beam of magnitude FH at the angle between the beam and the string is theta equals theta 1. The following rectangle represents the beam in figure 1. On the rectangle, draw and label the forces. Do not draw the components exerted on the beam. Draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted.
Now the average score for this question was 5.04 out of 12, which is 42%. This actually was the hardest FRQ on the exam for that year. So let's do it together and figure out how to do it.
So here is my free body diagram. There are three forces acting on this beam. The force of gravity of the mass of the beam, and we should always place that in the center. There's the force of tension, which has an angle, and there's the force of the hinge. So we know the direction of the first two forces, so let's begin by placing those on the free body diagram. Now we know there's going to be some force at the hinge. We need to think about what direction it's going to be on. The first thing that I notice is that the gravity force has no x component, but the tension force does. So there's a leftwards x component. And so we need to compensate for that. So the hinge force needs to have a rightwards x component. And now I need to think about, will the force of the hinge have a downwards component or an upwards component? We need to compare the up and down components of the two other forces. So we think about rotational equilibrium, the torque of these two forces should be equal. If we balance the torques, we get this equation, force of gravity times L over 2 equals the y component of tension force times L. If we rearrange this, we get this. Force of gravity is 2 times larger than that y component of the tension force. So because of how torque operates connected with distance, the gravity force is going to be larger and that y component of the torque is going to be smaller. That means there's an excess y force going downwards. So we need to separate our rotational thinking from our linear thinking. This hinge question is actually relying mostly on linear thinking. So the hinge force needs an upwards force so that there's no excess downwards y force that would push the beam downwards. So we'll say it has an upwards y force. Now this is heuristic thinking, so I don't know exactly what angle it's going to be at, but it's going to be some angle upwards to the right. If you draw 3 forces in the right spots, you'll do well, but to get a perfect score on that question, you need to draw the force of hinge in the right direction. And think about what's the excess force provided by those other 2 forces. Part B. The string is then attached lower on the wall at point 2. The beam remains horizontal, as shown in figure 2. The angle between the beams is now theta 2. The dashed line represents the string shown in figure 1. The magnitude of the tension in the string is shown in figure 1, Ft1. The magnitude of the tension in the string in figure 2 is Ft2. Indicate which of the following correctly compares the Ft2 with Ft1. So here is the same beam twice with the string at 2 different angles. And the force of tension is going to change. So which force of tension is going to be bigger? So the key insight here for me is that the y component of these forces must be equal. Because of torque, we must counteract the force of gravity.
Notice that it says, briefly justify your answer using qualitative reasoning beyond referencing equations. So the correct answer is that F2 is greater than F1. But qualitative reasoning means use words rather than equations. So we want to say something like this. The y component of F2 has to be the same as F1, but there's a much sharper angle. We know that these components need to balance because of the rules of torque. But if the angle is much sharper, then there's going to be a much greater horizontal component to F2, which means the overall magnitude of the force is greater. Here's the example answer they gave. In order for the beam to remain horizontal and at equilibrium, the torque exerted by the string must remain the same for all angles. When the angle decreases, the perpendicular component of the tension remains the same. Therefore, the tension in the string is greater for a smaller angle.
Starting with Newton's second law in rotational form, derive an expression for the magnitude of the tension in the string. Express your answer in terms of m, theta, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or equation from a reference book. Let's write down an equation. Newton's second law of rotational form is this. Net torque equals the moment of inertia times rotational acceleration. However, there's no acceleration in this case, so the rotational acceleration is 0. So net torque is 0. And that means the counterclockwise torque is equal to the clockwise torque. We can go ahead and put our various variables in there. We can cancel the L's, solve for force of tension. Part at a time. We have an equation for the force of tension in terms of the variables that they gave to us. Part D. Is your derived equation in part C consistent with your justification in part B? Explain your reasoning. So here we're going to get Ft equals Fty component over sine theta. So the only difference between these tension forces is not the y component, it's the angle that it's at. So as theta gets smaller, sine theta gets smaller, and that means force of tension 2 will be larger. As theta gets bigger, sine gets bigger, and that means that force of tension 1 is going to be smaller. So I could write this. Theta 1 is greater than theta 2, therefore sine theta 1 is greater than sine theta 2. Therefore, we are dividing by something bigger. Therefore, Ft1 is smaller than Ft2. E. The string is cut and the beam begins to rotate about the hinge with negligible friction. On the following axis, sketch the angular speed of the beam as a function of time for the time interval while the beam falls, but before the beam becomes vertical. Okay, here's the beam, the string is cut. Let's imagine a couple of different moments. So immediately, what's the angular velocity? That's going to be 0. So let's imagine the moment just after 0, and here it's going to be moving, but not very much. So we call it a small angular velocity. And then we imagine a moment right near the end. So it's almost all the way at the bottom. That's going to have a larger, faster angular velocity. The fastest will be at the moment right at the bottom there. So if I try and capture this, basically I'm going from 0 to a large angular velocity. So it might look something like this. Now, if you wrote this, you would get some marks because it's close, but not entirely right. The idea is that it's actually going to be accelerating more at the beginning because gravity is pointing downwards. It is perpendicular to the velocity at the beginning. So we could say here we get all the force of gravity pulling the beam in an angular direction. And then near the end, gravity is downwards and it's almost doing nothing. That is to say, there's only a tiny amount of force accelerating this beam when it's near the bottom. It's going to have a large acceleration at the beginning and a small acceleration at the end. So we need to put a curve on this graph to represent the acceleration is decreasing. Something like that. So we need to use physics reasoning to think about what will happen to the angular velocity of this beam.